Rechargeable batteries are made to do work again and again, which means they need to be charged after running out. The controlling system, the battery management system, needs to understand at which points the battery needs to be recharged to avoid damage of the cell, and at which point, usually a voltage, the charging needs to stop. This information measured and analyzed in the test labs of the battery company or research institution with whom they are collaborating with. A charge and discharge profile of a battery is usually measured as the voltage versus the percentage of the full capacity of the battery. This capacity is the normalized capacity of the battery after release. To avoid damage of the cell or battery, the charge and discharge voltages are limited. For an lithium iron phosphate battery, the maximum charge voltage is 3.75 volt and the minimum discharge voltage is 2.0 volt. These limits depend on the various chemistries of each battery and are adjusted to optimize the cycle life and lifetime of the battery, and as such included in the battery management system. The difference between the charge and discharge voltages depend on the internal resistance of the battery and are determined by various sources such as migration of ions in the electrolyte and reaction kinetics of the active species. The difference of the charge and discharge profile of a vanadium redox flow battery is also influenced by the pump power losses, but apart from all these internal resistances, we also would like to show why the discharge profile has such a curvature. This is easiest explained with a battery working with a simple dissolved species, as is the case in the vanadium redox flow battery. The discharge reactions that occur in a vanadium redox flow battery are vanadium 2+ ions to vanadium 3+ ions. The electrons that are being released go from the positive electrode, where vanadium 5+ goes to vanadium 4+, but this does happen in specific soluble species of vanadium, the oxyvanadium 5 cation or oxyvanadium 4 cation for vanadium 5+ and 4+ respectively. During the discharge reaction, the concentration changes as vanadium 2+ and vanadium 5+ will be consumed. The consequence is that according to the Nernst potential, the voltage will change. We also then need to know the state of charge, SOC, which reflects the capacity and which can be easily calculated by the fraction of vanadium 2+ that has been reacted, which is of course equal to the fraction of vanadium 5+ that has been consumed. A charge and discharge profile of lead-acid battery shows a significant difference in the charge and discharge profile, which is a result of various parasitic reactions that occur in the cell, as well as the internal resistance of the whole system, which is related to the complicated redox reactions at both electrodes. Despite optimization of the charge-discharge voltage limitation, degradation of the battery happens. This degradation is usually seen or experienced by the reduction of the capacity that the battery can deliver. The number of charges or cycles a battery can provide depends on how the battery is being used or misused. On the other hand, a number of 3000 cycles may be not even necessary for certain applications if the application itself does not survive the number of cycles. For instance, for a mobile phone that needs to be charged every day, then after 5 years you only had to charge your phone 1825 times, and 5 years is already long for a mobile phone, as it may be outdated in the meantime.